We're going to look at the resolving power of a diffraction grating, which is also known as the resolvance. The resolvance is written with this equation in the data booklet. Lambda divided by delta lambda is equal to m times by n. We need to define these terms. The resolvance, or basically the chromatic resolving power, is given the value, the letter R. Delta lambda is a difference between the wavelengths that need to be resolved. Lambda is obviously the wavelength of one of the wavelengths, one of the spectral lines. M is the number of illuminated diffraction slits, and N is the order of the spectrum. The interesting thing here is if you have a diffraction grating that has many slits per centimeter, then you're going to have a greater number of diffraction slits which are being illuminated by the light. So for two nearly equal wavelengths, lambda 1 and lambda 2, between which a diffraction grating can just barely distinguish, or the resolving power R is defined as R is equal to lambda divided by delta lambda is equal to m times by n. Therefore, a grating with a high resolution can distinguish between small differences in wavelength, and it depends on the number of slits and the spectrum order. For example, given a diffraction grating which has a certain number of slits have been illuminated, you will get a greater resolution, a greater resolvance, if you have a higher order spectrum. So for example, this is first order, second order, and the third order. It's quite clear that the third spectrum, the third order, will spread the lines out further, so it will be easier to resolve two spectral lines. Here's the equation again. Let's look at a problem. A diffraction grating has 20 slits illuminated. Find out if the grating can distinguish between two emission lines at 500 nanometers and 510 nanometers, which are resolved in a second order of diffraction spectrum. The way I would do this is find out what is the limit of this equipment. What is delta lambda given these parameters? So I need to rearrange it. Delta lambda is equal to lambda divided by mn. Let's put these values in. 500 nanometers divided by 20 times by 2. So we end up with a value of delta lambda as being 12.25. Now, in this question, they're 10 nanometers apart. And here they're 12.25. So this is not able to resolve these two lines because they're too close together. Now you want lambda divided by delta lambda to be equal to m times by n. So if they're equal, then they will just resolve the two lines. If lambda divided by delta lambda is smaller, then you will still be able to resolve comfortably the two lines. If lambda divided by delta lambda is very large, in other words delta lambda, which is the denominator, is small, very small, then you won't be able to resolve the two lines.